But yeah, fingers crossed we get a Z cross of 0.663. That'll be the one, because that'll be just a completely novel prediction, and that one will have to be looked.
Ladies and gentlemen, boys and girls, brothers and sisters, welcome back. Today I am sitting down with Blake Chateau. This is our second time we've got to meet. He's a forensic engineer out of Florida who embedded a Möbius strip into a three-sphere and watched constants of the universe fall out. And that's not really my summary, that's his, and it's called mode identity theory. And one of the things that you're going to find today that's going to be slightly different than most any of the other physics videos you watch is that October 21st, 2026, the Euclid telescope is going to be presenting some data. And honestly, for Blake, this date is critical, and we're going to come to that later on. But Blake, why don't you go ahead and let's get an introduction. Why don't you tell us a little bit about MIT or mode identity theory, and let's hear it from your words.
Yeah, I mean, you hit the nail right on the head. I mean, it's not really that hard, right? It's I took a non-orientable surface, right, the simplest one you can have in 3D space, and uh, totally geodesically embedded it into a three sphere, and just kind of flicked it and let it ring, and then just sort of saw where the calculations dropped out, and it's surprising, and so I'm just trying to get the work out there, trying to get, another set of eyes on it, some peer review, and kind of see where it takes me. And like you said, and you alluded to, for me, right or wrong, up or down, left, right, or center, supposedly it pumped out some graphs, some charts, and some numbers for the Euclid telescope. That's going to be dropping its DR1 data release 1 in October of this year.
Fantastic. And one of the things that you were just telling me before we came on and started recording was that you've just submitted another paper and you heard back in a quickness. You want to go ahead and fill the guests in what's going on?
Yeah, sure. I mean, so like, I'm kind of learning this stuff on the fly, right? I mean, I've been sort of like a bedroom DJ, bedroom physicist for some, I guess not really time, more of a DJ for a while. Then this physics thing is all of a sudden just accelerated exponentially, but we might get into that. But I'm still learning myself about how the process goes, and so basically, you can have a model and then give predictions, right? And so it'll predict this, that, or the other. And most of the time you're just left with predictions that have already been measured, or something that you can already see. And so the pre-registered predictions are things that you're saying, hey, this is what the data is going to be before it's even released. And so with Euclid, and I'm not going to pretend to be an expert on what Euclid's doing, but from what I can understand is, it's reading the redshift of galaxies, it's reading far back in time, and getting like an expanse history of the universe. And I use the word expanse because that's sort of the general thinking consensus is space is expanding. And that's what's giving redshift to all these galaxies and whatnot. And my model is saying no, space is finite. It's a volume. It's a specific volume. It's a specific size of a surface, and it's not that the surface is getting bigger or the space is getting larger, but just our perception as time goes on is giving the illusion of expansion.
So, and I'm gonna probe a little bit, and I don't expect myself to be as up to date on MIT as you are, but I'm going to try to ask a couple of questions that I think would be sort of fun to explore. So, when you're saying that there is a shape to this, early on you'd alluded to the Möbius strip, and you even shared last time a little life lesson that your physics instructor used to explain a Möbius lesson. I thought that was fascinating, and with that, if you can tie that together with what a 3D sphere is so that people can kind of wrap their heads around what you're trying to explain, because you're trying to say in this that physics has a shape. It can allow us to see things and make predictions on aspects that we don't normally see.
Yeah, yeah, and it really it goes back to Plato. And so in 300 BC, he's trying to make symmetrical shapes and then close them in on each other. And he's like, man, I can only do that to 5 different shapes, right? I can do a triangle, a square, a pentagon, etc. And even a triangle isocohedron, you can make it larger and all this stuff. But he's like, man, I can only get 5 of them. And that proof has lasted for 2 millennia now. And so what that kind of tells you is that there's like caked in geometry to our reality, right? I mean, there's shape to it, and there's specific shapes that can fit in it, and sort of the study of kind of like eigenvalues. And this is where I'm gonna I get a little rusty, but spectral geometry, kind of in a sense, is really like the vibrations of shapes, right? You give something a boundary condition and it vibrates, right? Like a lot of people are familiar with like maybe semantics and things like that, and it's this beautiful study of just vibrations and how boundaries can give shape or structure. And so at the grandest scale, eventually, that grandest structure is the Poincare homology sphere, or the three sphere, hypersphere, however you kind of want to slice and dice it. But it's basically a 3D orientable space that wraps back into itself. And so it's saying that you can have a finite volume of a three sphere, and you could be in that three sphere, and you can go in any direction, and you can go forever, infinity, just kind of like the Pac-Man scenario, etc. But instead of being a torus, it's a sphere, and since it's orientable, you're always going to come back to yourself. You're not going to be flipped upside down, inverted, or whatever. You come back, as yourself. And I always, that's what kind of like made me kind of breathe a sigh of relief, like kind of more of a breath in. But because working a lot with Mobius bands and Mobius strips, and it's a non-orientable, inverted kind of world where when you travel back and you get back to yourself, you're completely inverted and flipped, and you have to go all the way back around again to get back where you started. And so that non-orientability is a completely different property than an orientable surface, right? And so that's kind of where the topology comes into play, and then the embedding of it is saying, embed the surface into the sphere, and now you get sort of the best of both worlds. You get the orientability of the space, but you get the non-orientability of the surface, which is where we as humans are perceiving our reality, is fundamentally from a 2D surface. When you think about it, uh, your entire life, we've all just received information two-dimensionally, right? So we just see through the twist, we touch one dimension, we move in one dimension, and we infer the third. And so that inferred third dimension is the three sphere.
And then for the Mobius strip, how does inside of the three sphere, the Mobius strip is basically working as a as an as a perception or as a filter or as a realm of possibilities. How would you shape that role?
So I don't say easy. It's easy to me because I've been staring at this crap for months now. But you need a boundary condition, right? And so the three sphere, like I said, you can go forever, infinity, and come back orientable. But you need a boundary condition to start making some noise, right? Figuratively and literally, So to get a boundary, that's where the Mobius strip comes in. It's not necessarily for the surface. It is, but primarily it's for the boundary condition. It's that S1 edge. It's the edge of the Mobius strip. That's the sampling boundary. That's where the wave's at. And so it's really the boundary of Möbius that's embedded in the three sphere. And that's in the mission statement of MIT. S1 equals boundary Möbius embedded in three sphere. And the three
Yep.
sphere has no boundary, which is a very important part of that postulate as well. But that's a whole nother discussion. But at its core, that's what it is. S1 equals boundary Möbius embedded in three sphere. Everything happens on the edge.
Everything happens on the edge. And so um, when you explain your particles inside of this geometry, you get this almost falling out of this is where they're allowed, this is where they're not allowed. This is the boundary where these things can be found. Am I reading that correctly?
Yeah, the boundary is where the sample happens. And so you've got to sample the wave. And so it's literally you're sampling the phase of the wave. You sample at the boundary. Um, and then our perception of that is through the surface. I'm still kind of working on how I can better describe that and almost kind of even understand it better. This is kind of like a work in progress, obviously, but um, Yeah, particles, they're just they're realizations. They're modal realizations. Behind mode identity, mode in just its general sense is just it's a wave pattern. It's a specific pattern of a wave, and it ties directly back to de Broglie. RIP, man. I mean, but de Broglie is a cornerstone of my work. Wave matter duality, no, it's wave matter identity. Um, Matter is wave sampled. The wave is fundamental. The wave is going to be there regardless if we sample it or not.
So the wave exists, and at the sampling point, you get something substantial or a measurement result that allows you to have a particle at that spot.
Correct. Yeah, because time lives on the edge. So photons they're on the edge. They're massless. It's not until you make the observation, or you're starting to realize the matter. That's when the photon grabs onto the neutrino. At the base level. So there's a floor to it. The vacuum floor. It's cosmological constant raised to the fourth power. Oddly enough, it's like 2.25 milli electrovolts or something like that. But basically, it's a four-part equation. So you've got the floor, you've got the constant sunflower, which is it's like a Fibonacci type kind of finding your spot on the grid. Then you've got a Mackay elevator because I got to use things to help them make sense to me, right? So
Oh,
you got a Mackay system that's now like repping, right? It's doing I reps. And so it's repping until you can kind of get off at your floor. So the Mackay elevator kind of raises the energy until you hit the floor you want to get off. And then the last one's the Reidemeister torsion, and it's just like a torsion equation where you kind of spin out of the vacuum. That's kind of like, the doors open and the doves come flying out. That's kind of that little tweak to get you out. And all four of those parts of the equation, they're forced by the topology. There's not something I made up or this, that, or the other. They're forced topological consequences of the three sphere. And so it spit out an Excel sheet of 24 different weights. I looked at the standard model table, and the electron hit within 2%. Well, I mean, the table's there, and I'm just like, oh,
yep.
okay, cool. What's next? But that process happens on the edge, and yeah, it's pretty wild, man. I mean, just last week or this week, I'm still working on some cosmic microwave background stuff, and I'm looking at the pattern in it, and that same sort of spectral pattern. I'm doing Moline series that sort of captures that pattern. It's the same pattern that happens at the Yang-Mills mass gap level, of where you're starting to spectrally filter out, the gaps for matter and stuff. So I'm just finding patterns all in the work, and I just think it's the coolest thing.
It's fascinating. I think that I think that a couple of things that you've said here are fascinating to me. I'm wanting to poke a little bit deeper on the reason that you created mode identity theory. First off, what does that name mean to you? You started to surface it, and basically, we're looking through waves. Everything starts there, and that's the mode that it's in. And then go ahead and explain that. But go ahead, and I'd love to hear more about how did you come up with this? Like, what was your starting sequence? I know that you shared this with us before, but I would love to hear it from the get-go. Just like, here you are, you do a Google search. I think if that's where we start off, let's go with that.
Yeah, no, and it didn't even start off as like, hey, let me do a theory or anything. We were chatting about it last time, but I was just I think we're talking about work or something, and our company's he's buying out every engineering firm left, right, and center. And so I went on Google and I typed in, tell me about this company that we just bought or something like that. And accidentally typed it into the AI portion of it. On Google, it's like, ask AI or something. And I must have hit something. And I never had used it before. I'd never used AI before. This was in December of last year. And the AI said, "Oh no, that's how do you know that, right? Like where do you get your data from? How are you so sure of your answer?" And that kind of just kind of spiraled into just like this philosophical kind of thought experiment that I had with AI. And like within a couple hours, I was like, okay, I mean, like, is there any AI stronger than you? Because like, and so it's like, oh yeah, well, there's Gemini Pro, and I was like, are you just saying that because you're a Google product? So I'm like, I'm like just cut. I'm just kind of yeah, and I'm kind of tearing AI a new what, and so I got the Google Pro subscription, and then it still was more philosophical, and I just started thinking about what is knowledge, what's measurement, what's observation, what's realization, like And really, it all started with I wanted to put a subscript to the equal sign because I thought, if I'm making an observation, it's really not either a property inherent to either observer or either observed or observed. It's the act of just like coming into realization. And so I was like, why isn't the equal sign qualified? Right? Like, isn't there qualifiers to the equal sign? And so that that's how that started. And then just in my mind, in my head, I always was way first thinking. I was always thinking about dimensionality with scale, like with string theory. And the last piece of the puzzle was domain, actually capping in the domain. And so those are sort of like the three pillars of MIT is phase, dimension, and scale. And so those are really prior was to me just thinking of an equation, an observation needing three variables, and then kind of talk with AI. We got talking about what's space, what's the venue, what's the playing field that this is happening. So then I just took it from this as grand a scale as I could, and I said, yeah, I've always been fascinated with Möbius strips, Möbius bands. I've always believed that the universe started as a plane, as a surface. Um, and it just with those kind of things, with embedding, with scale, with the wave, it just it started to kind of pick up speed, and I'm going back and forth, checking this, checking that, and so by that time now I had like 4 or 5 AI subscriptions, $300-400 a month, all on Pro tier, and now it's completely tamed back. Now I just got one or two, just one or two because it's
Yeah.
I kind of have found my footing.
Yeah, I think that's great, and I think that that's, not an uncommon process. So, how does a guy who, on a day-to-day basis, is writing reports for, like, hurricanes and, roofs blowing off, how does that bleed into what you're doing today with MIT?
Um, I think it's great, and I'm thinking about like, yeah, like my line of work, is, I'm brought in a lot of litigation files, and so I'm constantly being deposed under testimony. I do courtroom witness, expert witness work, so I'm in the courtroom, getting asked, questions, and so I can't lie. I also have to tell you what makes sense to the most reasonable degree of scientific judgment, engineering judgment. And at the end of the day, almost nothing's 100% certain. But at some point, you have to call your shot, based upon the best evidence that you have. And so, um, when I was formulating and putting MIT together, I said I'm not going to ad hoc nothing. I'm not going to tune nothing. I'm just going to honestly see where this thing goes, right? And I'm going to be steadfast and determined with it. And so I think it's really well suited. The line of work I'm in, I think really helped me with MIT because it allowed me to be disciplined and honest, within the work that I'm already doing.
I love that. That's a great way to put it. Thank you. And so when you talked to me last time, you told me about your professor at Florida State. He takes off his belt, flips it around, puts it back together. I need to tell you, I love that story. I thought it was a great visual for all those people who haven't been in a physics class that is a well-taught physics class. Can you walk us through that moment again, just so that we get that live version of you explaining it?
Oh yeah, and I mean it should be taught in a physics class, right? And so a Mobius strip is a topological kind of like case study. It's a pure math kind of conjecture, or not even a conjecture. It just is because you can hold it in your hand, and so it's there. Since you can hold it in your hand, it's a really good description because we think we're in 3D space, but like our inferred perception of 3D space, we can 3D hold this Mobius strip, and it's not like really that Mobius strip embedded in this three sphere. It's actually a geodesic embedding. It's a little bit different, but I don't want to go sidestep. But you kind of asked me like, what's the whole point of all that? Because for years I had been doing math and geometry, math, all the math everybody else does, and then for engineering, we'd have to go with Calc 1, 2, 3, and then a couple years or a year of like diff EQs and stuff like that. And so it's a transition between Calc 3 and sort of differential equations. Is you're starting to learn about vector calculus, and you learn that vectors only can point certain ways, and that just was like a fact of life. It was as true as like natural numbers, 1 plus 1 is 2. You put two vectors out, and it's always going to be a orthogonal right hand rule, right? The right hand rule, and at the same time, we're doing Gaussian surfaces, electromagnetism, and physics class, in the other building, and it was awesome because like visually, I'm like, shit, man, like these triple integrals are like doing accounting for electromagnetism and stuff, and so it kind of really clicked, like I could see the math in my head or see the physics through the math, and it was super powerful when sort of that kind of clicked in my head. um and then my freaking professor took his belt off and he gave it a twist and hit it, and he's like, everything that you thought you had in your head and vector calculus, he's like, watch what I do. And he just ran his hand around and he said, that right hand rule that you thought was always up is not. And I was like, oh boy, did you just flip everything on your head? And from there, I knew the Mobius was extremely simple, and sometimes it's the simplest thing in the room that's the most powerful, right? And that darn Mobius band, dude, it does everything because that gives you your spin, that gives you your sign flip, that gives you half integer, it gives you all the spin mechanics of quantum mechanics in a simple freaking Mobius strip.
Yeah, absolutely, absolutely. Wonderful. So at one point, you were assigned some homework, and this is one of the things that I learned about you. You were assigned some homework for a three polarizer, and you said, "Okay, I've got this." So you went home and you just went to work. And go ahead and share what you did there.
Yeah, yeah. I mean, I always like doing Fourier transforms. So Fourier transforms taking an electrical signal, like an on-off or a step function, and just translated into a wave signal or vice versa. And so I just freaking love those problems, dude. I must have did every single one of them in the book. And then I had like another book. I did all those. And then I even went to like study sessions so I could get more of them little things to do. Cause I had to solve them all. Like it was like, I had to like, they're like Pokemon to me. Like I had to solve the biggest and baddest Fourier transforms because because they were the coolest problems, full stop. But, um, the three polarizers thing, and this was in physics class, and it was the whole thing, and it was like, so in my mind, I'm like, yeah, waves, they've got up and down EM waves and stuff, and I was like, so if it goes through a polarizer and then you turn the other one, like it can't physically go through it, it just ain't gonna work, and it worked. And I'm like, oh crap, another thing now that just blows my freaking mind. Great, like if the Mobius strip wasn't enough, now it's a dang polarizer that just blew blew that up. And so we had a take home test, and the take home test was just like, I don't know, solve a couple angles of it. But I found a website where you could type in any angle and it gave you like the percentage of what came out. And so I sat there for a week and I made my own quantum mechanical equation, just using probability using sine and cosine and the probability. And anyway, it turned out to be Malus's law, or
Yeah.
whatever it was, with the sine squared theta and all that. So somehow I reverse engineered Malus's law, but I kind of cheated because you could type in anything and then see it. But I mean, I guess it's the same thing as the experiment that you had. I mean, but yeah, to me, it was using waves, man. It's sine cosine, dude. They're powerful.
Very, very. And I think that the way that you use them is really interesting. So, one of the hardest things, and we started actually with this, is when we have physics that is starting to show up in the math, whether it be, in this case, MIT starting to show up in the math and letting us think about a flat plane and our 2D interactions that we then are able to project into 3D space. If we're taking a look at it in such a way, how would I explain this, say to my mom, say, hey, I just talked to a guy today and he was talking to me about a new way to look at reality that physics might actually be saying, drum roll. And then I intro to you. How would you explain this?
I mean, a fun one I like to do with my friends is, it's what do you think we live in, right? Like what kind of space? X, Y, Z. Three. We live in three dimensions, right?
Sure,
That's
that's a reasonable assumption.
okay. So it's like if you look, it's kind of hard because we're doing it here, but like let's say I want to go to this lighter, right? You'd say I'd go, X, Y, Z, right, to get to it. It's three dimensions. Well, no, it's not, because look, theta, phi, radial out. you can get to any point with 2 dimensions and 1 degree of movement or 1 dimension of movement. So what that tells you is we're not in 3 dimensions. You can get anywhere in 2 dimensions. Angle, angle, movement. Your entire life, you've only moved in one direction, radially to whatever your two angles gave you. So your entire life, you've been moving in 2 dimensions.
Interesting. I instantly go to the first time I ever tried to play the Nintendo 64, and it had two joysticks. One of them you always pretty much pushed forward, and the other one gave you your left and right directionality. In some ways, you're kind of describing the very first double stick joystick.
Yeah, it's kind of like holograph theory is big on it, like the ADS or CRT or whatever the heck it is. They're big into 2D because it's not just it. All of information is getting to us 2 dimensionally. Your eyes are the best receptor you have. They're 2 dimensional receptors. Everything else is a 1 dimensional reception, right? I mean, you've seen the little TikToks when you touch something, it's just a push back. This is F equals ma, but Newton's
Yep.
second law or third law. It's all everything you touch. Like I'm touching this lighter, I can only touch it 2 dimensionally. I'm reconstructing it having a 3D volume in my head, and the same thing is happening to all the information you're receiving through your eyes is you're getting it from a 2 dimensional plane, and then you're reconstructing the third dimension of it. It's just the true third dimension. It's an embedded dimension. We don't have direct access to it, and our access to it's through gravity. It's the price we're paying to kind of live on the edge, as I like to say.
Interesting.
It's a conversion of 3D volume to a 2D surface is where we're observing from.
Yeah, that's super fascinating. Thank you for that explanation. I like to kind of jump back and forth between here we are taking hypothetical, like how to explain it to our friends or whatever, and maybe we don't map it to a controller. We use holographs to try to understand it, which is awesome. But what if we take that back to now some of the things that actually give this credibility? We talked earlier that it's being reviewed. You've got peer reviews going on. Obviously, I've ran this through the AI engines that I've built that are there to design to catch math validations and looping logic and undeclared variables. And you've also done the same thing, ran it through, like you mentioned, multiple AI agents. But the thing that stands out to me here is you've got error bars, you've got percentages, you've got calculations that are all in theory reproducible, and you've got the GitHub repo up there that allows people to take a look at it if they have any questions. You've got your website, which is also very accessible. Most of this is all published. And by the way, I love the website, very personable, very relatable. And I love the fact that it's got a little bit of the Blake attitude just right there front
Yeah.
and center.
Thanks. I want to revamp the website completely and turn it more into like a journal kind of thing because it's just too hard to keep up with two platforms. But the GitHub is great, dude. I mean, my work is there. It's all in the open. I mean, I'm not. I got a couple little side projects, that I keep locally. But other than that, MIT's open source. I mean, the GitHub's right there. Go ahead, check it, run it, whatever. But
There you go. Go to the GitHub. All right. And so in the in the grand scheme of things, we're going to talk about the date now. What happens when, and I would love to be, if you wanted to, I think it would be an honor for us to get back together either right after this Euclid data comes out or, right before, or even if you wanted to do some sort of, live, just catch up. I don't know how many of your friends and family are going to be there wanting to, say, here it comes, but there's going to be a moment in time where you're going to be able to say, now I know.
yeah, yeah, and I mean, obviously, I mean, we'll catch up for sure. And there's a pre-release in June, and so I want to see how they release the data because then I need to take that data and then make sure everything's on the up and up and to where I put it in. I don't want to say conversion, but I've got an equation of state, I think as I call it. So like equation of state. And it's because I have to translate from, I don't want to say misconception, but misconception that we're in some kind of like fluid based 3D space. I got to transfer it back to mode identity theory. But with that being said, that the equation of state's right there. I'm telling you the equation. I'm telling you what the equation's going to say. let me see what's telescope's going to say, and just I'm going to run it right back through the equation and see if that in fact is what it said. But yeah, I mean, I got like a little group going. I mean, it's probably consists of my girlfriend and my daughter and maybe 2 or 3 friends right now. But like you said, I've got 2 papers in peer review right now with physics letter B, and so if those get published before Euclid and they gain traction, who knows? I don't know. I think it just would be an honor just to have those articles published because they, the one of them gives the phantom crossing, which is the kind of how the linear templates are going to say, oh, the redshifts going to go under z equals -1 or something like that. I'm just saying it's just an artifact of trying to fit a linear model to a cosine based wave in a nutshell. And then the second paper is the Mond acceleration scale. And so what I'm saying is the Mond acceleration scale is going to track with the Hubble parameter. They remain in lockstep. And so by doing that, that solves the James Webb early galaxy problem because it allows gravity to be stronger. And then it kind of tapers off and sort of follows the Hubble radius. So, or Hubble parameter, I should say. But and so those are the two big predictions is that as well as lambda is going to remain constant. So Einstein's cosmological constant is going to be constant because it's a fixed antinode of the wave. Hey, Winston. You
This
want a
must be your
brother and
daughter.
a sister? Yeah. You want to say hi real quick? Hi. Hello.
Hi. It's good to see you.
That's Mr. Adam.
What's your name?
Elowen, yeah, Elowen. Mm-hmm. Well, go see
Oh, and
Mama.
nice to
I'm on a
meet you.
say bye. I'm on a phone call. I'm just go hang out with Mama, and
It's
I'm gonna finish.
Why is that square over there with you?
Huh? Why is the square over there? Because we're talking. Me and two squares talking.
Yep.
Here, go with Mama. Okay, I'll be in a minute.
What
All
a
right.
cutie.
No, now she's putting me out,
Oh,
pushing me off the way. You're going inside with Mama, please. Thank you.
that's awesome.
All right.
That's awesome. I love it.
But
Did
yeah,
she
so
just get home from school?
yeah, so she'll be at the watch party.
Beautiful.
That's my
Beautiful.
that's my
That's the
fan group
one.
right
That's the
there.
one that matters.
Oh yeah, and it's great because I just love spending time with her, and I want to spend more time with her. So, the next best thing of being right's wrong, right? So, by all means, let me be wrong so I can spend more time with my daughter, right? So,
Yeah.
I
Yeah.
I could care either way. I just think it's fascinating that this is even happening. To where this model of mine is predicting stuff that hasn't even been tested yet, and it's going to be tested in a matter of months. So it's just incredible.
It's amazing time to be alive and an amazing opportunity to take a swing at something that could unify so many aspects of the way that we look at physics and give it a completely new understanding. So that is super exciting. And I'm really excited to see what happens here coming up with the Euclid announcements and the data that comes in. That pre-release data, that's going to be exciting. And you'll be
Yeah.
able to start mapping that. You'll kind of get some gut instincts on which trends are going to be catching and which ones are maybe going to need adjustments. Who knows?
Oh, no
But I
knobs,
think it's
no knobs
no
here.
knobs. I know. As I started to say it, you can hear it in my voice. I'm like, adjustments. Wait, we don't got no
No,
knobs here. There's no
not
real
MIT.
adjustment.
No. There's no
No,
knobs
that's
I can
great.
turn, man. There's really none. I mean, sure there might be some template thing, but I mean the equations, and that's been my thing the entire time. I don't want to knob anything because I'm not here to turn it into a living trying to instantly turn knobs all the time. You know what? LCDM. Like I just want here's the model. Is it gonna take or break?
Yeah, absolutely. Absolutely. Well, I sure appreciate your time. I appreciate getting to learn about this MIT work. I appreciate being able to expand my perceptions on how reality could be shaping itself. And I appreciate all of that you've been able to bear with me. Like I said, this is episode 1.5 because the first episode was technically challenged. Um, Blake, how about yourself? Is there anything that you wish that you could just throw out there for the universe to hear you say and share with whoever might be listening and finding this?
No, it's already ringing. It's gonna be ringing, and far after we're out of here. We're gone, and we go where we need to go. But yeah, fingers crossed we get a Z cross of 0.663. That'll be the one because that'll be just a completely novel prediction, and that one will have to be that.
that will definitely make some noise, like having that land. So again, I appreciate it, my friend, and I hope to catch up with you in the very near future.
Absolutely.
And
We'll
with
do
that,
that. Yep. Thank
we'll
you.
be talking soon. Thank you so much, everyone. Thank you for joining in. And if you'd like to see more of Blake's work, you can find it on theoryofeverything.ai, his website. I'll have all the links in the description. Thanks, everyone.
All
Thanks,
right.
Blake.